estimated, but makes their estimation hard. Basically what happens in this case is it's no longer complete data, so you need to do this loop, EM loop. Okay, and in particular, in fact, you can ask yourself, why did we get into this looping aspect? You showed us the likelihood estimation. This is still ML, by the way. This is just maximum likelihood estimation. So why couldn't we just take the maximum likelihood, expression and optimize it? You could do it. What happens is that you'll see in a minute that essentially, actually I can show it in a minute. Yeah, why does EM work? I'll come back to the rest in the next class, I guess. Basically what you have is this J is the hidden variables. And when you are maximizing likelihood, you need to maximize the expected likelihood while marginalizing the J out. You're trying to maximize, you are trying to say the likelihood of the data over the different possible distribution of the hidden values. Because hidden values were never part of the data. There is no point in talking about likelihood with respect to the hidden variables. Okay, so what you would wind up doing is you would be maximizing this expression. The thing that you should worry about this expression is there is a log, of course it's a log likelihood, but of a sum. It's no good to have sums in logs. It's good to have products in logs. Because products in logs become sums, and then you can use the simple separation of derivatives over the sums. If you have products, then essentially this is you don't expect to be able to find analytical maximum for this likelihood. Okay, so instead what you wind up doing, so log of sums don't have any easy closed form optima, so what you will wind up doing is you use something called Jensen's inequality, which essentially says arithmetic mean. One way of thinking about Jensen's inequality is that arithmetic mean can never be less than the geometric mean. Okay? Now if you do that, then basically, so you start with this, and then you write this guy by doing FTJ by FTJ, where FTJ is an arbitrary probability distribution over the hidden variables. It's a probability distribution. Okay? So if you do that, then using the Jensen's inequality, you can take this guy and you can bring out you can take the log inside. So basically you can push the log inside. In this case, you have FTJ log of this. So this is expected value, because FTJ is a distribution. So expected value of this guy with respect to FTJ. And that would be always less than what you're trying to compute. Okay, now this one has the right form, sum of logs. This one has the wrong form, log of sums. Okay, because it has the right form, it's like, why is the drunk searching for keys under the street light? You know the story, right? I mean, you see a drunk searching for his lost keys under the street light, so you also start trying to help him. And at some point of time he says, so did you lose this here? He says, no, I lost them somewhere there. He said, why aren't you searching there? Because there's no light there. I'm searching here because there's light here. This is not where I lost the keys at all. Right? This, you should know this. We do this all the time. Okay? What we really wanted to do is optimize this guy. But there's no light there, because you cannot do derivation, differentiation easily over log of sums. So you find a nice little bound. Now you are ready to go. You can actually optimize this. Okay? So this is a beautiful picture. So what you have, this guy might look like this. Some arbitrary log likelihood function. Now you can directly do gradient ascent on this. Of course, that's possible. Okay, but what we are doing here is we are now finding a bound to this at every point. So if you are here, you found a lower bound function. Okay, so this function here is going to be guaranteed to be a lower bound on this. So this is this function. Now for this function I can compute the optimum analytically, because it's in the right form for me. So I can do MLE. In fact, notice when I recompute the model, basically I'm just doing MLE estimates. And I'm assuming that those MLE estimates are cheap. Okay, by just taking, in Bayes networks, for example, they're actually quite cheap because you just take the counts. Okay, so you know this is the lower bound, right? One of the interesting things is if this is the lower bound, then you know that wherever this is becoming maximum, will still be lower than the real maximum. Right? So if you are going to make a step, I would say you should make a step on x-axis up to this point. And since you know how to optimize this using analytical techniques, you'll find the optimum, which is what you do in the M step, in the EM, expectation maximization, in the maximization step. So you compute the ML likelihood and you find the parameters for which the lower bound becomes optimum, and you use the same parameters to evaluate the upper bound, evaluate the true function. So basically this will be your new guess now. And you see the likelihood with respect to new guess. And then you compute the lower bound again here. It will look something like that. And then you take the upper bound, the maximum there, of that lower bound again there. And then at some point of time you will reach here. Okay? Now, this is why actually EM is also called, it's a stepless hill climbing. Stepless hill climbing. Normal hill climbing requires a step size. Okay? And so normally, for example, a gradient descent requires a step size. You need the gradient direction, and in this case you need gradient ascent. So you need the gradient and some alpha times the gradient. That will still work. Okay? And an even better idea than normal gradient descent is Newton-Raphson, which essentially takes not only the first order derivative but the second order derivative. And it changes the x value by xn plus 1 is xn minus f dash by f double dash. If you can compute those two, then you can make a step of the next step you are getting. By the way, this f double dash is why the Hessian, I mentioned a couple of times back that when you do function optimization, sometimes you have to do a Hessian. F double dash is the Hessian for the multidimensional case. Okay. Instead of doing this, which will still work by the way, EM algorithm actually is doing this. It looks more natural for us because, notice that this picture is just as good as a description of what is happening what's happening in EM as the previous example where I took the complete data to learn the parameters and then use that to complete the holes, and then I took this recompleted data, more complete data to learn the parameters again and recomplete the data. Every time I complete or recomplete the data, I'm doing inference. Every time I learn the parameters, I'm doing maximization because I maximize the likelihood. That's why it's called expectation maximization. And the idea of maximizing the log likelihood still holds. It's just that people do EM. EM has become popular because for this scenario, for this particular case of a bad log likelihood, Jensen's inequality helps you to find a lower bound and you can optimize that lower bound analytically oftentimes. Okay, this will always work. In fact, you could do EM just by doing, actual climbing of this likelihood. But it's pretty hard because you are essentially having, even getting an estimate of the gradient is going to be hard in these cases. Okay? So think about why this is all connected to k-means clustering. So for example, if I told you in this case that there are two educational possibilities, PhDs and undergraduates, then you would have done that. You would have essentially done k-means basically by finding exactly two clusters. Okay, and think about the fact that normal k-means, for those of you who thought about k-means before, who learned k-means before, in normal k-means, in every iteration, each data point is categorically assigned to a cluster. It's called hard assignment EM actually. K-means is called hard assignment version of EM. EM on the other hand keeps the distribution. When you complete the data, you don't give it a value. You give a distribution for the missing value. And according to this distribution, this missing value might be 0.3 of this cluster, 0.7 of this cluster. So it adds 0.3 to the numerator of this cluster and 0.7 to the numerator of this cluster. Previously it had either 1 here or 1 here. Okay, that's the difference between K-means and EM in the clustering scenarios. But EM also can be understood in general as learning base network configurations with hidden variables. Okay, we'll stop here. We'll complete some do's ends next class, and then I guess the class after that is sort of an extra class, sort of in between December 1st, and then the last 2 classes are going to be presentations of the projects.